All right, so tonight's topic is going to be binary arithmetic. So we left off last class talking about signed binary numbers, and now we're talking about, okay, now that we have our numbers, let's see, once the numbers are there, we're going to now learn how to perform arithmetic on binary. So again, re-emphasize, this is not a math class. This is a computer science class, and we cover math insofar as how it's implemented in a computer. All right, so we'll keep that in mind because you'll hear me say that a lot. So with binary arithmetic, the very first thing is addition, right? So when you do any type of addition, a computer is going to break down an addition problem into one of these four base cases. All addition problems are one and or more of the following steps down here. So you have 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. These are the four possible base cases of A plus B, right? So these are the four possible A plus B base cases. So all binary arithmetic is going to be one of these four problems. Okay? So so far, any questions? Anyone who sees this and say, oh my gosh, this is super hard. I hope not, right? This should be very straightforward. If anyone's shaking their head right now, you are in trouble. All right. Now,
are we a class behind from the other section?
Yeah, because you guys had no class last Tuesday, right? Because of Friday schedule. So that's why you shouldn't be comparing notes with the other class, because they operate at different paces because of holidays. All right. So if you attend only the other class or get notes on the other class, then, again, do so at your own risk because the classes are not identical. All right. So with that said, now with addition, we have, if you're dealing with a single bit addition, that was one of the four base cases. But what happens when there's more than a single bit? In this case, there are 4 bits involved, right? Where A is 4 bits. Let's look at the example on the left. It's 1011, and B is 4 bits, 0010. So given this, a computer, when it does math or addition, it doesn't see the entire number. It doesn't have to. It looks at the number and says, oh, that's nice. But when it proceeds to do the problem, it does it in pairs. It does this pair first, right? 1 plus 0. So 1 plus 0 was one of our base cases. 1 plus 0 is going to give you 1, right? And then what happens is it moves to the next column. Then it does in this column now. 1 plus 1. So 1 plus 1 was 2, right? So 2 was 0, and it carried a 1 over to the next column. Okay? So basically, what I'm trying to emphasize here is when you do math, binary math, it doesn't look at the entire problem. It breaks A and B into pairs. So it does A, the first bit of A and first bit of B, and moves on to the next pair. So it does it pairs at a time. All right? So looking at both of these, essentially, it will just do both of these additions. It'll add it up, and you'll get these numbers. So within the parentheses, I put in the value in binary, right? 1011 is 11, 0010 is 2. If you add together, it's 13. So this is just in case I still have anyone on this meeting that is still not familiar with 4-bit binary, but there it is, like a little cheat sheet. All right, so because of the way that computers do math, there's some requirements built in. The first being is the number of bits in the input must be the same. So what does that mean? That means A plus B. If A is 4 bits, B has to be 4 bits because it adds things based on pairs. So that's a requirement, is the input sizes have to be the same. So what happens when they're not the same? For example, if the top was written as 1011 and the bottom was written as 10, if this was just a math class, you could do it, right? Because what you're instinctively doing without doing it is you're putting zeros down here. You're padding it with zeros. So that is exactly what's happening here, is that if you don't have enough digits, you pad it with zeros just so that the top number A and the bottom number B have the same number of bits. All right, so that's one requirement. The other requirement is, because the computer is doing this and it's doing things in pairs, is that the number of bits in the output will need to be the same as the input. So why is that? Let's think about this. When you were programming back in Java or C++, if you declared a short value, like a short variable, and two shorts, if you add two shorts up, the result would be a short, right? Same thing, if you add two ints up, the two ints would be result we stored in an int. And just the same thing, if you add two longs, they wouldn't end up being a long. So when you declare the size of the inputs, when you do addition, the output is expected to be the same size. Okay, so for addition, input sizes have to be the same, and the output will be the same as the input. So if you look at this, I have 4-bit inputs, and my output is 4 bits. So that begs the question, what happens when you add two numbers, and instead of being 4 bits, the answer is now 5 bits because it's larger? So that brings us to a topic of overflow. So overflow is a very general term in computer science. Overflow just means that it overflowed or overfilled what was capable of being stored. So for example, if you have 4 bits, the largest number you can store in 4 bits is 1, 1, 1, 1, which is 15. So what happens when 15 plus 1? 15 plus 1 is 16, right? So that won't fit. So that will be an example of an overflow where the answer, if it was just math, you could do it. But keep in mind that you have to be able to store the answer. So because we're doing computer science, and especially hardware architecture, storage becomes important. It's no longer the ability to do the problem, but the ability to store the answer to the problem. All right, is that clear to everybody? So when we're dealing with hardware architecture and computers, you have to deal with the possibility of overflow where the answer is bigger than what you can store. So in this example, you see on here, the top number is 14, the bottom number is 11. If I added it using a computer and chopped it off at 4 bits, the answer is 9. And you say, wait a second, how come it's 9? The reason it's 9 is because this one over here, we had nowhere to store it. So that was overflow. Okay, so again, overflow means that the data does not fit in the space provided due to finite storage. So you might say, well, why can't we just make it 5-bit storage? Okay, fine, because that's why you have shorts and you have int. A short is 16 bits, int is 32 bits. And if it doesn't fit an int, you can use a long. Long is 64 bits. But it's still the same concept is what if you have two longs, you add it and it doesn't fit inside a long? Well, then you make it even bigger. So again, that's not a problem, but each time you make it bigger, there's always the possibility of the biggest number you can think of. I can always make it bigger by adding a larger number to it. So eventually, because you're dealing with finite storage, the concept of overflow will exist. May not exist as often if you use larger data types, but they do still happen. Okay, so again, that's what overflow is. Like very general concept just means that data doesn't fit in the space provided. All right, any questions? All right, so our next screen, I have 3 problems over here. All 3 of these exercise problems have a problem. Identify what the problem is and do it, or do it and identify the problem afterwards. However you want to do it, but just go, give you a few minutes, work on all 3 of these. Again, this is not a math class so that you can do math. This is an exercise, see what you understand how computer would process this. All right, give me a few minutes. Okay, so let's do this together. So the first problem we see there, we have the issue where the A and B aren't the same size, right? So the computer, when he looks at this, will need to make a correction and say, okay, this will need to be padded. All right. So basically that needs to happen first. Then once you do that, then this is just regular using the base cases. So this is 1, this is 2 with a carry, and there we go, done. All right, next is 1, 1. 1 plus 1 is 2. So I carry a 1 over, so 1 plus 1 again is 2. So with this one, we have overflow, right? And this problem, let's say 2, 2, 2, and 1 plus 1 plus 1 is 3. So this also has overflow. All right, so the last two problems have overflow. And the first one, the inputs sizes are not the same. All right, so if you get a problem like this, you would need to identify that these are indeed problems that need to be addressed, or at least acknowledged, instead of just doing it and say, oh, that's a math problem. Again, this is not a math problem. This is a math problem as it relates to how a computer does it. All right, so now let's move on to subtraction.
So we have to indicate that there is overflow?
Yeah,
okay.
Because if you don't, the answer is wrong, right? Do you understand?
Yeah, I understand.
Okay. All right, so subtraction. Subtraction also has its base cases. So 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1. And then the last one, this is very special, 0 minus 1. And you might ask yourself, how can you take 1 away from 0 and get 1, right? That doesn't make sense. And you're right, it doesn't make sense. This is a special condition. This last base case requires a concept called borrowing. Okay, so what does borrowing mean? So remember back in, like, I don't know, maybe first grade, second grade, you have a problem like this. Let's say 11 minus 9, right? Remember how to do that? 1 minus 9, you can't do it. So what did you do? You borrowed. So this became a 0, and you borrowed the 1. So now this becomes 11 minus 9. 11 minus 9 is 2, and then 0, right? Something like that. So that's the same principle here, except it's in binary. So how does that work? So let's go through the steps. When you borrow, the computer looks at the first pair again, right? 0 minus 1. And once it sees 0 minus 1, say, oh, this is a borrow base case. So what does it need to do? It now needs to look to its left to see a number to borrow from. So it's going to go here, here, and here and say, okay, there's the one I can borrow from. So once it finds that one, what it's going to do is it's going to change the values, flip the bits on the way back. So 1's become 0, 0's become 1, and then the last digit is now a 2, right? So 2 minus 1 is 1. And now the next column is now 1 minus 0. So 1 minus 0 is a base case, is 1. Next is 1 minus 0 is 1, and 0 minus 0 is 0. Okay, so this requires borrowing. So next example here. This is an example where you're borrowing twice. So how does this work? It does the first column and realizes 0 minus 1, I need to borrow. So what's going to do, it's going to look and see I can borrow from over here. So this becomes 0, this becomes 1, this becomes 1, and this becomes 2. So 2 minus 1 is 1, 1 minus 0 is 1, 1 minus 0 is 1, and now I have the same problem again. I have 0 minus 1. I can't do it. So I have to borrow again. So where am I going to borrow from? I look to the left, and it's all the way down here. So this becomes a 0, this becomes a 1, 1, 1, and now this is 2. So 2 minus 1 is 1, 1 minus 0 is 1, 1, 1, 0. Okay, so borrowing, just like in real life, is a pain, right? That's called a practical example. Borrowing has a stigma attached to it. You don't want to borrow because borrow requires keeping track, just like in real life, requires keeping track of, like, you know, where you borrow from and all the people that you had to ask. So this is what happens, is when you borrow here, not only do you not just take from the next door, but you have to keep going every single column until you find something that has something to borrow from. And then you have to keep track of how far you went, and you have to flip all the bits on the way back, right? Look at our second example, is that every single bit had to be flipped. So not only do I have to keep track of how many bits I had to go down, I had to change the values. Once I change the values, then I have to go right back, go one column at a time. So borrowing is a relatively expensive operation in terms of performance, right? When you're doing addition, literally it's just one column from the right to left, one at a time. But with borrowing, it's entirely possible to go one column, move 3 columns down to borrow, move 3 columns back, do the base case, base case, base case, and then borrow again, back, back. So again, it's a lot of bookkeeping involved. So you don't want to borrow if you don't have to, okay? So give you 3 exercises to do. Some require borrowing, some don't. So just do this just so you can get the hang of it and realize you really don't like to borrow. And then just like everywhere else, we'll find a faster, better way of doing this. All right, so spend a few minutes, do these 3 problems. Okay, so let's do this together now. All right, the first one, 1 minus 0 is 0. 1 minus 1 is, I'm sorry, 1 minus 0 is 1. 1 minus 1 is 0, 0, 1. Okay, that's the first one. So no borrowing needed over there. Here it's 1, and this requires borrowing. So 0 minus 1, I can't do that. So I borrow from its neighbor. This becomes 0, this becomes 2. So 2 minus 1 is 1. 0 minus 1, I can't do that again. So I need to borrow. So 2 minus 1 is 1, and this is 0. Okay. Next one over is borrow, right? So this is 0, 1, 1, and this is 2. 2 minus 1 is 1. 1 minus 1 is 0. 1 minus 0 is 1, and then 0. All right. So 2 of these on the right require borrowing. The first one didn't. All right. So now let's move to multiplication. Multiplication also has base cases. So you multiply here, you have 0 times 0 is 0, 1 times 1 is 1, and then 1 times 0 is 0, and 0 times 1 is 0. So these are the base cases for multiplying. When they're a single bit, super, super easy. But reality, though, is that what happens when the number is larger? What if it's 2 bits, right? What if it's something like this? So when a problem is like that, then what happens is that you do this first, right? 1 times 1 will give you 1. And then changing color here. And then 1 times 1 again will give you 1. And then you would go to the next column and do 1 times 1, and you put over here, right? And you pad with a 0. And then you finish with this, gives you 1. And then you add, correct? So essentially, when you are multiplying 2 bits or more, it's not just enough to multiply, but you have to add up the products of the multiplication. So for each number of bits that you have, you're going to have a row that needs to be added up, right? In this case, A and B were both 2 bits. So because there's 2 bits, you're going to have 2 rows to add up. Okay, so let's take a look at a larger example. Here, I have 1011 times 0011. So because there's 4 bits, there are now 4 rows that needs to be added up. Okay, hopefully it's very still straightforward, right? This is the exact same rules as regular multiplication, except you're multiplying 1s and 0. But once you multiply 1 and 0, you still have to do the sum and add it, everything up. All right, so is anyone seeing anything on here that is blowing you away, saying, oh, I don't understand this? This hopefully isn't tricky. Compared to regular multiplication, this should be easier because only 0s and 1s. Any questions so far? All right, so now let's look at some requirements. Just like how we talked about addition, the input size need to be the same thing for multiplication. When you multiply, your input sizes should be the same. However, your output now is different. With the output size is going to be double the input size. So whatever size your input is, you have for storage purposes, you have to allocate twice as much space. So let's try to understand why it's twice as much. So let's do this chart. Let's say input bits max input max product, and then the number of bits involved. Okay, so we're going to have that. So let's start off with a base case. This one we can, if the input size is 1, the largest value is 1. So the maximum product is 1 times 1 is 1, and 1 can be stored in 1 bit. All right, that's too easy. Now let's do 2. If 2 bits, then the maximum input is 1, 1, right? And that value is 3. So it's 3 times 3 gives you 9. So 9 is 1001, which is 4 bits, right? All right, now let's do, if the input size is 3 bits, that means the largest input value is 3. 111 is 3 bits. 111 is going to be 7. So 7 times 7 the largest product would be 49. So 49 in binary would be, let's see, would be 110001. So this is 6 bits, right? Now let's do, if it's 4 bits, that means that the input value is 1111. That's 15. So 15 times 15 is 225. So 225 in binary is, oops, hold on, let me clear this. 225 is going to be 111 0000001. Okay, and that is 8 bits. So do you see the pattern here? Input size and output size. Is that the relationship between your output bits in relation to your input bits? Is that, look, it's double. All right. So as a general rule, when you're doing multiplication or building a circuit to do multiplication, whatever your input size is, you have to allocate the double number of the bits to store the answer. All right. So how's that in practical terms? Is that when you multiply an int and an int, you end up with a long, because longs are 64 bits. All right. Okay, with that being said, let's go back to the slides. All right, so now let's move on to integers. Integers, remember we covered in our prior class, is when you have signed numbers, positive and negative. So for signed addition, unless it's specified, it's generally assumed when you're doing arithmetic, it should be 2's complement. So if we look at the values here, 1011 plus 0010, and then we just did addition based on our base cases that we covered 15 minutes ago, we end up with this result. So if these values are unsigned, the top number would be 11, the bottom number would be 2. If I translated the answer, it's 13. I say, yeah, that's exactly what I expected. However, prepare to have your mind blown away. What if they're not unsigned? What if I told you that, you know what? Let's pretend they're signed. There's 2's complement. So the top number 1011 would correspond to -5. And 0010 would correspond to +2. If you added it, you looked at the answer, it's -3. And you're saying, wait a second. The addition works both ways. It doesn't really matter. The rules that we learned for binary addition work whether the binary is encoded using unsigned or 2's complement. Regardless which value, it works both ways. Okay, so that's good for you because you don't have to remember 2 separate algorithms for addition. Whether it's unsigned or 2's complement, you follow the exact same rules because they both work. Okay, the rule works for both unsigned and 2's complement. You end up with the right answer. Okay. All right. So signed addition, fantastic. Now let's talk about subtraction. With signed subtraction, now we're going to say, hey, remember this formula back in maybe 5th grade? You can rewrite a minus b and you can change it into a addition problem by changing the sign of b, right? Because b is an integer. So instead of a minus b, it can be written as a plus -b. So by changing the sign of b, you are able to change an addition problem, change a subtraction problem into an addition problem. And then once an addition problem, then it's just the same rules. Remember we covered 2's complement or unsigned, addition problems are all done the same way. All right. So now let's take a quick segue to figure out, well, how do I change from b to -b? So assume that b is 0101. This is +5. Okay. So how do I get, if I have +5, how do I get negative in 2's complement? Remember, it's flip the bits and add 1, right? So I would flip the bits. This becomes 1010. have to add 1 to it. And this is -5. All right. So this should be a review of our 2's complement, right? The top number is +5. The bottom is -5. To get from positive to negative, I just flip the bits and add 1. So now comes the question. What if I start off with -5? I got to get the negative of that or the opposite sign of that. How would I do it? How do I get it back to +5? Well, good news. You don't have to remember any new rules. To flip the signs, you always flip the bits and add 1. Watch what happens. Flip the bits. 0, 1, 0, 0. And you add 1. Do you see that?
Well,
Yeah, mine is blown, right? So if you have positive, doesn't matter if you have positive or negative number. Remember, to flip the sign, it's always flip the bits and add 1. All right? Does this example make it clear for you? All right, so whatever the number B is, if you want to change its sign, you flip the bit and add 1. Okay? All right, so now that you know the flip the bit and add 1, give you some exercises. These are 3 subtraction problems. What I want you to do is change them into addition problems and add them. All right, so it requires, you don't want to flip the bits and add 1 to, so this is A minus B. You only want to flip B. You don't want to flip A. So change all these into addition problems by changing it to A plus -B. Okay, so only B is flipped. All right, give you a few minutes, work on these 3 problems. Okay, so let's do this one. The first one, 1 0 1 0 1 1 minus 0 0 1 0. So this has changed to this problem, 1 0 1 1 plus 1 1 0 1. And now I flip the bits, now I have to add 1 to it. So this becomes 1 0. Okay. Now I add it. This is 1, this is 2, 2, and this is 3. Okay, so
Sir,
yes.
could I ask one question?
Go ahead.
For that first one, don't the zeros in the front of the number on the bottom, the 2, don't they not count? So aren't we adding?
You got to flip the whole, again, matching pairs. So you flip it. So 0 0 1 0 becomes 1 1 1 0. Okay, so this becomes 1 1 0 1 plus 1. That's 1 1 1 0. Okay, that's what we have.
So it's technically a padded number, but we still consider all the zeros.
Yes, it's a part of the number. Correct.
Okay.
Remember we said before, matching pairs. If A is 4 bits, B needs to be 4 bits as well. Got it?
Yes, thank you.
Okay. All right, so once we do it, then you look and say, aha, we got overflow problem, right? Which, yeah, it does look like it, but here's something interesting. The top number, if it's 2's complement, is negative, and this is -5, right? The bottom number is negative, let's see, 0 0, -2. This is -7. It's like, wait a second, you have overflow, but the answer is correct. What's going on? Must be a coincidence, right? All right, we'll assume it's a coincidence for now. Let's do the next problem. The next problem, 1 1 0 1 minus 0 1 1 0. So this number, if I flip the bit, it becomes 1 0 0 1, right? And I have to add 1 to it. So this becomes 1 0 1 0. Okay? So I rewrite the problem to 1 0 1 0. Adding that, this becomes 1 1 1 2. And you say, looks like we have overflow again, right? Looks like we have an overflow. So let's test it. Let's see what the answer is going to be. The top number was negative, let's say 0 1 0, this -3. The bottom number was negative, let's say 1 0 1 0 1, that's 5 plus 1 6. -3, -6. And the resulting answer is +7. And we're like, aha, looks like it's overflow, right? Which is, yeah, it is an overflow. So good. So it looks like we had an overflow bit and the answer is wrong. So we said this must be overflow. Okay, so now we're going to do the last problem. One 0 0 0 minus 0 0 1 1. Okay, and this gets changed to 1 1 0 0 plus 1 is 1 1 0 1. So we rewrite this into an addition problem, 1 1 0 1, and add it through 1 0 1. And we're like, oh, looks like we got an overflow problem again, right? So let's see the top. This is -8. The bottom is -3. And this is +5. So you say, aha, looks like we have overflow. So definitely this is a problem. Okay, so far so good. We see 2 of these have overflow issues, but technically the first one had overflow as well, but the answer was right? So how do we reconcile that? Is it just, dumb chance that it worked? Well, here's the answer, is that even though all of these 3 examples had overflow, like physical overflow, the way we defined it, that doesn't necessarily make the answer wrong. Okay, so here are 6 problems. So no need to flip the bits, because now I know you know how to do flip the bits and add 1. So these are 6 problems. They're just plain old addition, but these are adding signed numbers, which means that there's 2 complement numbers that represent it. But we already discussed that, right? The same rules apply whether it's 2's complement or unsigned. It's the same rules. So I want you to add all of them and give me the answers. And after we do that, let's figure out which ones are right and which ones are wrong. And then see if we can find a pattern, because that's what computer science, right? Underline the word computer science. It's not computer, computer, building or computer software. This is computer science. So science has a scientific method, right? Where observation, you try to find patterns. So in our prior slide, we showed that the overflow there doesn't necessarily mean the answer is wrong. So now I'm giving you 6 problems to do, and some of these will have overflow, some won't. But we're going to try and figure out how can I tell there's an error or not by looking at the number. Okay, so give me a few minutes, do all 6 of these problems, and then we're going to review each answer to figure out if we can determine how can we tell there's going to be an error inside this answer without having to know what it translates into. All right, so have at it. Give you a few minutes. I'll grab some water.
Yes, sir.
Be back in 5 minutes. Yes, question.
Are we thinking about these in 2's complement?
Yes.
Okay. All right. Thank you.
Professor, in the previous slide, the middle one, that was the answer was 10101 with overflow. That was it. Middle
Yeah,
one?
they had an overflow, right?
Yeah, but it was 10101, right?
I don't remember because I erased it already.
Yeah, it was.
It
All right,
was?
just
All
do this current slide, please.
Thank you.
Okay, so let's do this now together. The first problem is if we add it together, this is 0, 1 plus 1 is 2, 2, and this is 1, right? So let's look at the number. This is positive 6, this is positive 2, and the answer here is negative 8. This is obviously wrong, right? But there's no overflow. That's odd. Okay, let's do the next one. This is 1. 1 plus 1 is 2. 1, and this is, this one has overflow, right? So with this, we have an overflow right here. So let's see, this is going to be negative, and this is negative 5. The bottom is negative 1, 0, negative 6. And the answer is positive 5, right? So we say, so this is overflow. So obviously this shows this is the wrong answer as well. Okay, next we have 1, 1, 0, 1, 1, and say, looks like I have overflow again, right? So this top is negative 3. This is negative 0, 0, 1, so it's 2. And the answer is negative 5. And we're like, wait a second, there's an overflow, but the answer is correct. All right, let's do the next one. This is 0, 0, 0, 0, 1. And we say, there's an overflow here. So the top is negative, negative 1, and this is positive 1, and the answer is 0. So this is actually correct, even though there was an overflow. It looks like, but it's correct. All right, so what's going on here? So with this one, this is 1, 1, 1, 0. So this is positive 5. This is positive 2, and the answer is positive 7. So this is correct. And the very last one is 1, 1, 1, 1. So this is positive 7, and this is negative 8, and this is negative 1. So this is actually correct. Okay, so all 6 of these problems that we've done, 4 of them looks like we got the right answer, 2 of them are wrong. But notice that 3 of them had an overflow, right? But out of the 3 that had overflow, 2 out of 3 were correct. So what's going on here? So just using this sample of the problems that we did, was it fair to say that an overflow bit doesn't necessarily mean it's wrong? Because 2 out of 3 times it was correct, even though it had overflow. All right, so you'll try and find out what's happening. The problem is that when you use 2's complement, even though there's 4 bits involved, when you use 2's complement with 4 bits, when you have 4 bits, you have the first bit is used for the sign. And then the remaining bits are your magnitude bits. Okay? So we have 4 bits. The leftmost bit is your sign bit. The remaining bits are your magnitude. So the largest positive number that you can store is 0, 1, 1, 1, right? And this corresponds to positive 7. Now, if we look at the first problem here, positive 6 plus positive 2, what should that store? It needs to store positive 8. Can you store positive 8 using sign magnitude? I'm sorry, using 2's complement? You can't, right? Because with 2's complement and 4 bits, the largest positive value is positive 7. So you ran out of bits. Does everyone understand that? So even though there's 4 bits here, only 3 of them are used to represent your magnitude. So I can't represent, even though I can represent positive, negative, but I can't represent the value positive 8 because positive 7 was the largest. So this is still technically overflow, but it's not a physical overflow because it fits in 4 bits. This is more like a logical overflow because how I'm using the 4 bits, because the leftmost bit is used as a sign. So effectively, I only have 3 bits left to represent the value. Okay, so it doesn't fit in the 3 bits that I allocated. So this is a logical overflow. All right, the next one is -5 plus -6. The result is -11, right? So using the largest negative value that I can store is using 4 bits is 1 0 0 0, and that's -8 is the largest negative value. I can't store -11. So the same problem again is that I can't store a value there. So how can I tell there's overflow? So here's how you do it. How can I tell there's logical overflow? Is I look at the signs. Look at the problems that are wrong. Notice that I have a negative number plus a negative number. Look at the sign of my output. It's positive. When we add two negative numbers, you end up with a positive. You know that you have an overflow issue. Same thing with if I add a positive number to a positive number and my answer is a negative number, I know there's an overflow. Does everyone see that? I don't even need to convert anything over. Once I do the math, I look at the signs of the output and the input, I compare it and I say, oh, my inputs are positive, my output's negative. Overflow. That's it. No need to do anything else. Okay. Now let's compare it to the problems that are correct. Notice that this is negative plus negative, and the answer is still negative. Hence, you have the right answer. Same thing for this one. Positive plus a positive, you end up with a positive. Okay? So, for sign addition, overflow errors are detected not using the extra bit. So the presence of this bit is meaningless in sign addition. Overflow is identified by looking at the sign bit. Does everyone understand? You look at the sign bit, if the sign is the same, you're good. If the sign is now different from your inputs, you have an overflow issue. So that only has one thing remaining now to cover. What if the inputs aren't the same sign? If you're adding a negative number to a positive number or a positive number and negative number, right? Well, in both cases, when your inputs are not the same sign, you don't have to worry about overflow because overflow cannot exist when you add a positive to a negative. Because when you add a positive to a negative, the resulting number is always going to be smaller. Okay? Understand that. When you add a positive to a negative, the resulting number is always smaller, so you never have overflow. So overflow cannot happen. Overflow only is possible when we add 2 positive numbers, when we add 2 negative numbers, where the magnitude gets larger. Okay. Any questions on overflow detection? All right, let's move on to multiplication.
So is the overflow detection that we were using to as like there's an extra bit, do we just not need that?
You don't need it. You know, we just say it's irrelevant, it doesn't work.
But even earlier when we were doing
Or earlier, well, this is why I mentioned is signed, right? This is signed addition. Earlier, we were not doing signed addition.
Okay.
Got it?
Yep.
This is an issue because we're dealing with signs. The prior one's unsigned, there's no sign bit. Okay, now for sign multiplication. So sign multiplication, unfortunately, is not going to be the same as regular multiplication. Because with sign multiplication, if we multiply this through, this would be oops, hold on a second. The top number is -5, the bottom number is +3. If I multiplied it, my expected answer is -15, right? So if I multiply this straight through, like how I normally did it, you know, I would end up with something like this. Okay, so this is not going to be -15. There's no way you're going to make that -15. All right. The reason sign multiplication doesn't work is because if you're dealing with sign multiplication, positive, negative number, there's at least two different ways of doing it. There could be more, but we'll talk about two different ways. The first way to attack a sign multiplication problem is by a method called sign extension. Sign extension just means that I need to first extend the number of bits, pad them. So on my top example here, this is +5, right? 0, 1, 0, 1. If I put an infinite number of zeros in front, it's still +5. All right, everyone agree? I can put as many zeros as I want in front of it, it's still +5. It doesn't change the value. So now, what about negative numbers? This is -5, right? So is this -5 if I pad it with a whole bunch of ones? Is that still -5? And the answer is yes, that's still -5. How? If I want to get its value, I say this is negative, and to get the magnitude, I flip the bits, 0, 0, 0, 0, 1, 0, 0, +1, and that would be 1, 0, 1. And that's 5. Okay, so sign extension just means you extend using the sign. So if it's positive, you pad it with zeros in front. If it's negative, you pad it with ones in front. So how does this apply to multiplication? Well, the original problem I had before from -5 times +3, all I did here was pad it with ones, pad it with zeros. So I doubled the inputs. All right. Remember we said about multiplication, the input size and the output size. The output will be double. So for a sign multiplication, you just double the inputs. Once I double it, then I multiply it straight through. Now, if I add it, 1, 1, 1, 1, and then I can chop it off there because I don't care about the overflow. If you look at this answer, this is -15. Okay, so sign extend, if you're dealing with signed numbers, you have to remember to sign extend it to multiply. If you're dealing with negative numbers, that's one way of doing it. So now we're going to talk about the other way. This is one way, is sign extend it, and once you sign extend it, you just multiply it how you normally multiply, and you'll get the answer. The other way of doing it, it seems more complicated, but it's actually a little easier. So the other way is multiplying this positive absolute value. So that sounds like a mouthful. So essentially, this is what it's doing. Remember back in the day, if you had a problem like this, -5 times +3. Back in algebra days, this is what they made you do, right? You multiply 5 times 3, and you got 15. And then you determine the sign. Then you say, okay, once you do it, then look at the sign. If both the signs are the same, it's positive. If the signs are different, it's negative, right? So you broke the problem in half, where you multiplied the magnitude, and then you multiply and then figure out the sign afterwards. So in binary, there's a similar concept here. But what you need to do is first, everything needs to be converted to positive. You need to make everything positive first. Okay, so looking at this, we have 1011 times 0011. The top number is negative. So I need to make everything positive. So the top number is -5. I convert it to +5, flip the bits and add 1. I would end up with this, right? +5. And the bottom is already positive, so I leave it the way it is. Okay, so now I multiply that through 1010, 0101. This is 1, 1, 1, 1, 0. And then of course I double the number of bits, right? And do I stop there? No, because I need to convert it back to negative if necessary. How do I know I need to convert to negative? I look at the signs, right? If the signs were the same, it stays as positive. If the signs were different, I make it negative. So because the signs are different, I need to make it negative. So this answer I have, I make it negative by flipping the bits and adding 1. So this becomes 1, 1, 1, 1, 0, 0, 0, 0. And I plus 1 to it, right? You plus 1 to it, this becomes 1. And if we look at this answer, 111001, same answer. Okay, so these are the two ways that we can do multiplication. So learn both of them. They have different advantages and disadvantages. And more importantly is when we cover digital circuits, we're going to be building a circuit that does multiplication. And you're going to say, oh, this method is easier than the other one for implementing using circuits. Okay. All right. So do we have any questions on binary arithmetic? Anything about the topics we covered tonight? All right. If there's no questions, then thank you, everybody. We will see you on Thursday. All right. Have a good night.
Thank you, Professor.
Professor,
Yes.
just a quick question. Do you think we could find like some practice problems besides what we have on the slides?
No, you can look at the work sets. I think the work sets have a few problems on there.
Where could we find those?
They should be on the website. The class website, Blackboard.
Oh, the Blackboard. Because I didn't see any. But do you know under what category they might be?
Well, there's only so many links on there, so please have a look first. Okay. But they should be on Blackboard.
Professor?
Yeah.
I'm on Blackboard. There's only 3 categories: homepage, announcements, and syllabus. I don't really see anything.
There's no documents.
No, there hasn't been anything at all. for this-
Okay, I'll take it out later.
Okay, thank you.
Okay, no problem. All right, any other questions? All right,
Thank you.
if there's no other questions, yeah, I'll check it out. Hopefully it should be on there. If not, I'll find out what's going on. But
Yeah, I
the
just-
work
I
set is
just
going to be
went through the-
due. I'm sorry, it was a question?
Yeah,
And
so
I'll see. Oh, go ahead.
someone asked if we can, if there's practice questions in the textbook.
No, I don't think so. No,
Okay.
there might be, but I didn't really look for it inside the textbooks. All right. So the work sets, I believe, have some of them, but I'll check on it to see why it's not available. But the work sets aren't going to be due in probably another 2 weeks, usually right before the exam.
Okay.
Okay. Any other questions? All right. No questions. See you guys Thursday. Have a good one.